Hello, everyone. I'm going to get started here. So my name is James Strassburg, and I am the senior architect at my company, Direct Supply. We're based out of the Midwest. And I'm here today to present some research that I've done on tuning relevance in solar using genetic algorithms. I've got a lot of slides here, and I have a demo at the end. So if you would please hold your questions to the end. We're the last session, so we'll have time. Or you can feel free to connect with me on the app. So the agenda of what I'm going to talk about today is how I approach looking at my search engine algorithm as an optimization problem. I'm going to take all of you through a high-level overview of what genetic algorithms are and how they work. I'm going to talk about how I found a way to model my solar parameters and encode them for the genetic algorithm as a potential solution. And finally, I'll talk about how to define a fitness function using analytics that's stored right in my solar database. So when I was doing research on this, there seems to be some interest as I found a few blog posts, but there weren't too many detailed explanations of how to do anything. So I did find one very vague blog post on using genetic algorithms in this way, and I thought it had a very funny comment, which I'm going to try to solve here, but it was, I am from Indonesia and want to build search engine like a Google and want to build a system using genetic algorithm, but I am confused, what will I do first? And this was, it wasn't the broken English that was funny so much as it was a comment on a blog post of how to compete with Google. So I thought maybe I'd do a little bit to try to help this fellow. I hope he's not here. So in looking at your search algorithm, there's many different types of parameters that you might be adjusting. So with a simple select query, we might have a couple of query fields that we're looking at, name and description, which could have associated boosts alongside with them. We could have phrase fields, phrase slop values, min, should, max. A boost function, again, with a boost value associated with it. And of course, there's many more things you could have as part of your algorithm. So when I first deployed solar, where did all those numbers come from? And that's the truth. I made them up. And then we did some testing and we tweaked them and nudged them up and down. But really what struck me as we were doing this was that even as our understanding of how the different parameters worked grew, this method of just guessing and then nudging things up and down felt very unscientific. So with a set of numbers like that, how do we know that we've found the best set of numbers for our given algorithm, or even a good set? And I'm proposing that this represents an optimization problem. So I have a link to my GitHub on the end of the presentation, which contains, the GitHub contains the implementation that I've done, along with a sample schema and configuration of solar. And the example that I'm using as part of this implementation is an example that came right out of the Great Solar in Action book. So I didn't come up with this on my own, but we have two fields in the schema, name and description, and we're going to store restaurant information. And in it's used in the book as an example of when you might want to apply a boost value to a field that you're querying. So in order to make this work, I also disabled length normalization because the name field is going to be much shorter. And I wouldn't recommend you do that in most cases, but just for the purposes of this simple example, it makes everything work. So the data set, again, this comes from the Solar in Action book. The data set is two restaurants, Red Lobster with a description of we deliver the freshest caught seafood every day, and another restaurant, Joe's Crab Shack, with a description of we serve delicious red crabs, rock crabs, large lobsters, and other delicious seafood. Our lobsters are our specialty. And with the search that's at the bottom is a search for the phrase red lobster. And if we do nothing else, Joe's Crab Shack shows up first because of the number of hits for red and lobsters in the description. And it's just a very simple example where you apply a simple boost, a very small boost to the name field, and you get the order that you expect. So let's talk about genetic algorithms for a few minutes. Genetic algorithms are a tool for solving optimization problems. We have a set of data, it's a very large search space, and we want to optimize the results. I'm not contending that it's the only solution to those types of problems, but it's one that I've been very interested in and what I used here in this research. So they're based on ideas from genetics, evolution, and natural selection. And we'll get to a little bit more of that in a second. And then the development that I did is using an open source library called DEEP, Distributed Evolutionary Algorithms in Python. And it's a library that supports many different types of genetic algorithms, and then within those, or different types of evolutionary algorithms, and then within those different implementations for things like selection functions and crossover functions. So in order to implement a genetic algorithm, we've got to, first of all, define our candidate solution encoding. So a candidate solution is going to be a potential solution to the optimization problem. And if we're talking about the set of numbers that we're using within our search algorithm, we've got to encode that somehow. Binary encoding is the most popular, and it's the method that I used here. It's not the only method, but as you'll see when I get into that, if you straight binary encode floating point numbers into a long string of bits, you'll run into some problems. You have to define a fitness function, which is just that, just one function, which takes a candidate solution and outputs how well that solution solves your problem. Then the algorithm engine will generate an initial population of random solutions. It will select candidates from that population, not at random, but with specific functions for reproduction. We use then crossover and mutation, which I'll talk about in just a second, in order to create a new child generation. And along the way, we're measuring fitness. We're measuring fitness in order to determine the likelihood of selecting individuals from the population for reproduction. And then as we get to the next generation, we'll do the same thing again. And then we repeat this until some criteria is met. And that criteria could be you ran it for a specific number of generations, you got to some pre-specified level of fitness that you were hoping to achieve, or you ran out of money or time. So crossover and mutation are two operations that are kind of the keystone of the genetic algorithm. So let's say we had selected two parents, and this is just a binary encoded number, or a binary encoded candidate solution. We selected two parents from our initial population that we wanted to use to reproduce into a child generation. So there are different types of crossover algorithms. One of the most popular and one that solves a very complicated problem is two-point crossover. So as you can see here, the third and the fifth bit are being exchanged from parent one and parent two to produce the child. And then there's a mutation rate, which in this implementation is just a bit flip. And there's going to be a probability that we're going to mutate a specific bit in the child sometimes. And the whole reason for doing that is just in case our initial population did not contain some characteristic that we ultimately need in our optimal solution. Now, like I mentioned before, we need to figure out how we're going to encode parameters. And since I'm using Python here, Python's floating type is double precision, so 64 bits, and that's the huge range we've got there. And 64 bits, if you had 10 parameters, would be a lot of bits. So I decided to look for a better way to encode the parameters. There's a NumPy library that Python has, which supports single point floating point numbers, and also 16-bit, or what I'm calling half single, because I don't know if there's actually a term for that. And then, as I was thinking about it, I thought about a situation like this, where we've got two select queries, and we're looking at a field. And since the boost values are floating point numbers, I could say field boosted by 35.2 or field boosted by 35.3, and those could be two different candidates. And I decided that those were too close to really care about. So I was looking for a mechanism to really trim down the size of my encoded candidate solution value. And I came up with what I'm calling decimal Fibonacci encoding. After I get through this, you might find that if you were going to do this, you'd want to have either more or less precision, and you can obviously do that. And really the point of this is just to show to what extreme you could trim down the encoding of your candidate solution. So with the solution I came up with, I decided to use the values 0, and 0 special because if we end up with 0 as a value and it was a boost value, I end up removing it from the algorithm rather than boosting by 0. 0.2, 0.4, 0.8, and then I start counting up the Fibonacci sequence. 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and 144. So if you counted all those, that's just 16 different values which will encode very nicely into just 4 bits. And by having a small encoded value, we can get very fast evolution. Because you see, as the numbers get bigger, we are amplifying the amount that the difference between the values makes. Whereas if we had a full floating point number, maybe we flip a bit, and now we're at 35.3 instead of 35.4. Also, this will, by having not so great a precision, this is going to help us avoid zooming in on local maxima when we're optimizing, and hopefully find a global maxima because we're not so ingrained. And the specific bit flip operation or mutation is going to have a much larger impact. So just to show how those would map, 0.0 becomes 0.000, all the way up through 144 is 1111. So for encoding a candidate solution for the problem, that's the example where we have name and description. Let's say we had a candidate solution of 0.4 as a name boost and 13 as a description boost. That would become 0.4 becomes 0010, 13 becomes 1010, and our candidate solution is just the full binary string with those two concatenated together, 0010, 1010. So now that we've figured out how to encode our parameters, we need to define a fitness function. So what the fitness function is going to do is measure how well a particular candidate solution solves the problem. And it should be very fast, because maybe if our stopping criteria is we're going to run it for 1 million generations with an initial population of 1,000, we're going to need that thing to be pretty fast. And one thing earlier that I didn't note about Deep, the library that I'm using, is the D is distributed, meaning it's designed to be distributed across a cluster. So the first mechanism I investigated for measuring fitness was normalized discounted cumulative gain. And if you haven't heard of this before, it essentially says very relevant results are better than relevant results, which are better than not relevant results. Pretty straightforward. Relevant results are more useful to the user if they appear earlier in the results. So the first result is better than the 10th, even if it's on the same page. And the results themselves should be irrelevant of the query or the scoring of the results. So if you have two different queries like cheese versus 1969 red Corvette convertible, one of those is going to be more difficult to search for. So normalization helps mitigate that. So a quick example of how you might implement this is by showing somebody a set of search results. And a while ago, I learned that the classic LA punk band X, just the letter X, released a box set, and I learned this from a coworker. So I went to Google and I typed X box set. And I couldn't find, it was all video game stuff that came back, obviously. And I found out if you add CDs onto the end of it, that it actually came back as the 4th hit, an Amazon link. So in implementing normalized discounted cumulative gain, you might show somebody these results and ask them to rate them as not relevant, relevant, or very relevant, and you might set a score for each one. And if you take each of those scores and add them up, you'll get the cumulative gain. And then if you want to discount based on the position. We end up dividing by effectively the log of the position, and that will help make higher results worth more than lower results, and that's your discounted cumulative gain. And then finally, to normalize it, you would do this for the entire set of queries that you're using in your implementation, and then you'd find the ideal value and divide all the scores by that, making the best of the best have a value of 1, and then everything else is normalized to be somewhere between 0 and 1. So the problem that I thought I'd have with this was that if I actually had a person involved in doing this, and I was trying to do this many times, maybe even 1,000,000 times, it would be far too slow. So there's a potential that you could do this ahead of time and try to gather this information and store it, and then use it later in your implementation, but I didn't have it. So the next method I looked at for developing a fitness function were related to precision and recall. And again, if you're not familiar with these, precision is the likelihood that a returned result was correct. So if you have some understanding of what's a correct result versus what's not a correct result, you can establish precision. It's calculated as the number of correct results divided by the total results. And recall, the likelihood that a relevant result was returned in all of the results that were returned. And correct results over correct results times missed results. So now we've got two values that we're measuring, and while the distributed evolutionary algorithms in Python library does support doing multi-objective genetic algorithms where you can try to maximize or minimize two different values, I stumbled across something that was more interesting and actually made it a little bit better, I think, and that's the F measure. So the F measure is defined as the harmonic mean of precision and recall. And the way the harmonic mean differs from the arithmetic mean is that the harmonic mean tends to punish outliers. And it's a pretty simple computation, 2 times precision times recall over precision plus recall. Now what struck me with this algorithm are two things. First of all, now I'm back to a single objective genetic algorithm trying to maximize F measure. But since this calculation tends to punish outliers, if I had a candidate solution that had a very high precision and a low recall, it might skew the results into something that was more even, balanced, and pretty high. So I ended up implementing this. And then I also took the idea of discounting results from the normalized discounted cumulative gain. So now I have another problem, which is how do I know that these results are correct or not? And I decided to crowdsource this from the users. And this is an idea for collecting this. You might already have this analytics, but I added a field directly to my Solr document, which I'm calling search term interactions. And it's a multi-valued field. And if you actually implemented this, you might choose to put this in multiple fields. But how you define this is completely up to you. But essentially what this means is that you had a positive interaction with this document for this specific search query. And for an e-commerce site, some of the ideas I've had for adding to this array would be somebody did a search and then they clicked on a result and went to see the product detail page, or maybe they added something to their cart or ended up ordering it. So with the example that I have in there, I've added Red Lobster, if you recall, as a positive search term interaction to the document that is Red Lobster to help drive the algorithm. So now, if I can get it up there, we're going to show a demonstration. Let's see. Visible. Just wanted to show a little bit of code here. I don't know if it's going to be legible or not, but you can get this all off of my GitHub. And what this is an implementation using Deep, the library, which runs against my local Solr that I've got deployed with the sample schema that I've just talked about. And you can see a little bit of how this library works. We're defining that we're looking for a maximum instead of a minimum value. You tell it kind of how to create individuals in your population. The evaluate here is where I tell it, this is my fitness function, candidate solution.evaluate, which crossover or mating function we're using. In this case, we're using CX2 and this library supports lots of different ones. The mutation algorithm that we're using is a flip bit, and the probability 0.05. The selection algorithm for selecting individuals from the population to create a child generation from, we're using something called tournament selection. And with tournament selection, if this was tournament size equals 2, a good way to explain it is you pick 2 at random, and then you evaluate their fitness, and you pull a random number, and if the random number is, say, less than 0.75, if it was between 0 and 1, if it was less than 0.75, you might use the fitter individual, or choose the fitter individual. If it's otherwise, you'll choose the less fit individual. So it'll skew it towards more fit values, and that type of function prevents you from having to test the fitness of the entire population in order to get a probability. Here's my initial population size is 200. And one thing, a feature of genetic algorithms that I haven't talked about yet, but is implemented here and I used it, is the Hall of Fame, or in genetic algorithm lingo, it's also called elitism. And what it is essentially keeps track of the best solutions that it ever saw when it was processing. So I'm telling it here to just keep the best one you ever see. And that has been shown to drastically increase the performance of genetic algorithms. This line is where it actually runs, and we're telling it to run here for 10 generations, and then it prints out the best solution. So if I run this here, it's actually going to run, as part of the fitness function, it's calling back to Solar to figure out, or actually it's getting the results each time. It's doing a search and then using that to measure the fitness. So I don't know if I can, will that show up? It does show up. All right, so I have Solar running. And if I run this, it'll start going, and we'll see Solar's flying. So after 10 generations, I don't know if I can zoom down here. Yeah. And because this is a very simple example, the values for the name boost are kind of all over the place. If I run this a few times, you'll see a few different ones, but it's going to routinely eliminate the description from the search engine in this case, since I'm only searching for red lobster. But the name boost is going to vary quite a bit. Here's a 0.6 with a description boost of 0. It's been fairly consistent. My initial implementation, I was actually taking 0 and just applying that as a boost. And it seemed to work fine for a while until it hit the answer of 0 for a name boost and 0 for a description boost. And then red lobster came back, even though the scores were actually 0 for both of them. Yep, 5 and 0. So yeah, feel free to take a look at this code on GitHub if you want to start playing with this type of stuff, because it's pretty interesting to me. And where I'm at my company is I really want to apply this to our data, so we're starting to design the implementation of collecting the analytics data that we need in order to really run this against our data set. So at the end of the slides, there's a few resources, links to the deep library, and the link to my GitHub repository if you want to take a look at this, and a link to my Twitter. And I believe I have a few minutes left for some questions if anybody has any. I was kind of afraid I was going to run out of time, and I think I flew through it, so I probably tripped over something. Yes? Can you repeat that, please?
Yeah. You switched from log of result rank to F-score, F-measure.
Yes.
Talk a little more about that information.
Yeah, he asked of me switching from log of result rank, essentially part of the normalized discounted cumulative gain, to the F measure. And I am actually I'm still discounting the values with the F measure. So if you look at my fitness function, I'm actually doing a discounted F measure where I'm calculating the precision and recall and then discounting the precision based on where it returns. So the correct results, but it's skewed by the log of the position. If I was going to do this with multiple search queries, I would probably normalize them as well. So I really like those ideas from normalized discounted cumulative gain. Like let's say you had analytics that told you your top 2,000 search queries, and you wanted to use that as the input to the algorithm. I would probably normalize those F measures so that they weren't different from query to query as I was trying to find the best candidate solution. Because then the execution of the fitness function is going to spin through each of those potentials that you want to try, or some subset of them. Yes?
Can you go over again, not the formula, but how does the system know whether or not a document was relevant to a query? Did you manually tag those or true matrix or something? Or the precision of recall, you still have to know whether it's a good match or not.
Yeah, in my implementation here, if I back up a little bit, I added a field to my schema in Solr with the idea that I would kind of crowdsource the information from my users. And I called it search term interactions and made it multi-valued. So that's right alongside my schema. And what I'm saying is, if a user then does something that I construe as a positive interaction with a document based off of a specific search query, I can go back and update the document in Solr and just collect it like that.
So an implicit tag marks a document as being relative to the search. That's what you use for precision and recall to feed that into your evaluation formula.
Yes. Yes?
Can you apply this genetic algorithm in conjunction with the domain knowledge of the data? So it searches for a specific domain, and you use this to further refine the search results.
Sure. So he was asking if, could I use domain knowledge to further refine the search results or change the algorithm? And I think definitely you could implement however you want. And one thing that I thought of right off the bat, if you remember, I used the example of like the min should match at the beginning. That's not going to be a floating point. So you might have a completely separate encoding mechanism for that type of parameter versus a boost. So it might encode boosts like I did, because I'm only using boosts in the example, but if you did a min should match, like you could skew it that way. And you might already have some information about. So like I said, initially, you come up with your algorithm, which has all of your values that you've defined, and you've done testing and you've nudged things up and down. So you have an idea of where things should be. I would probably actually take that knowledge and probably cap a range of the search space for each specific parameter. And that would be another way of encoding them such that you could reduce the size that you're going to have, the number of bits you're going to have in the candidate solution for that specific thing. Maybe you only want to try a range of 5 different values for a specific value or parameter. Yes? I think he has a microphone. You can get him recorded.
So the values you get at the end of the genetic algorithms probably depends on the terms you select for the training. So did you do any experiments on how it will generalize in the other queries, like for the terms that you didn't use to calculate the fitness function?
Yeah, it's based off of whatever data that I would have, and kind of the idea of crowdsourcing that analytics information from the user base would be in hopes that I would get a very large set of it so that I could do it for a wide range of queries, or my top 50 or 100 or 1,000 queries that I experience. Yes?
Have you run this on larger examples? And if you have, about how long does training usually take?
He asked if I'd run this on larger examples, and if I have, how long has this taken? And I have not. I'm hoping to, at the beginning of next year, run this on our actual search engine implementation deployed where I work. But we need to do a little bit of upfront work to collect some of the analytics information. And we've also got a bit of an issue with data normalization, because our e-commerce search engine is comprised of data that we receive from many different parties. And things like categorization, our content is not very good, to cut to the chase. And I'm afraid that if I run this against that data set without doing some work to clean it up and normalize things like category names, that I'm going to get myself in, I'm not going to have a very good result. But I do want to run it. And I'm hoping that the fact that the deep library can be distributed that I'll be able to find a way to do it relatively quickly. All right, we are out of time right now, and I'm happy to hang around. It looked like there were a few more questions. I'll hang around down here because we're the last session. If anybody wants to come up and ask something, otherwise you can feel free to connect with me in the app or on Twitter. Thanks.